Good morning, everyone, and you're very welcome to day two of the AtlanTec Festival. It's our 7th year running, and this is the week packed full of events with over 60 speakers. My name is Ian Gallivan, and I work in the Innovation Office in NUI Galway, and I'm delighted to be your host for today's session. We're on all the social media channels. You can follow us on AtlanTec Festival, AtlanTec Fest, sorry, on Twitter and the hashtag AtlanTec. Of course, we wouldn't be here today if it wasn't for the continuing and generous support of all our sponsors, whom you can see here, who year on year never fail to support this festival and bring us this wonderful opportunity to meet and discuss these topics. So today, I'm going to be talking with Venkatesh Kannan on the subject of quantum computing. So today's speaker, he's a Centre Technical Manager at the Irish Centre for High-End Computing here in NUI Galway. Venkatesh has been at the forefront of iTech's drive into quantum computing. Today, Venkatesh will be talking to us about the evolution of quantum computing from what we probably all thought of as something abstract to something that is now very much in the here and now. He'll be giving us a broad overview of what quantum computing is and taking us on a journey around the major industrial players in the space and showing how the EU and Ireland are putting forward frameworks in place to encourage and develop the adoption of quantum computing. As Venkatesh talks, you can pose questions at any stage. I'll be monitoring the question and answers function. You'll find it on the bottom right-hand part of your screen behind the three ellipses. Just pop it open. Anything that crops up on questions and answers, we'll deal with after Venkatesh's talk. So at the moment, I'll ask you to sit back, relax, enjoy Venkatesh's talk, and over to you, Venkatesh.
Thank you very much, Ian. Hello, everyone. Welcome to today's session. Hope you're all having a very good morning. So as Ian pointed out, we can discuss basically today a quick overview of why quantum computing is so much prominent in the news and research topics these days, and where Ireland and Europe are generally positioned and where we are headed in terms of developing the technology and its applications. So, okay. Yeah. So I've basically structured our conversation today around three elements, starting with a quick overview of why quantum computing has been in the news and why it's relevant in terms of technology and its applications, and also look at some of the key areas in which development has been very prominent and is going to be really important. I mentioned I insist key because some key areas because the development in this technology is across the entire spectrum, right from the fundamental science to applications and end use. So it's possibly going to be a huge endeavor to cover all of them in any detail, but we'll highlight some of the key that are going to be essential, and also what's happening in the space of quantum computing, particularly quantum software and programming in Ireland. So in terms of quantum computing itself, it's been a technology that's been in science and theory for a good few number of decades. Why it has been becoming more prominent these days is that the practical realization of quantum mechanical devices that can perform quantum computing, quantum communication, etc., they are becoming more and more practical these days. And where does quantum computing sit in the general notion of computing technologies? Well, it's kind of the fifth generation, so to say, of computational devices, starting from vacuum tubes, and more recently where we are at is in terms of silicon semiconductor-based microprocessors. Quantum computers are expected to be the next generation or iteration of how we do computation. And so far, researchers are yet to fully bring this technology out of the lab, so to say, into practical applications in our lives. However, in the past 5 years, for example, there has been rapid development in the technology in creating quantum devices. The software and hardware capabilities have improved tremendously. And with that comes now a promise of actually realizing a quantum future. And industries that could benefit most out of quantum computing technologies are envisioned to be in sectors like in healthcare, in manufacturing, in pharmaceuticals, and so on. While machine learning and cryptography have indeed, and AI have been mentioned as one of the few of the areas where quantum computing has the potential, they are reliant on this technology scaling up over time to be able to address larger problems. And that's pretty much why quantum computing now is more and more relevant, because of the ability to realize these devices in practice. Oh, okay. Yeah. So in terms of quantum technologies, this is not the first time that we have been working with these technologies. The first quantum revolution was a good few number of decades ago, when, for example, based on the quantum mechanical effects and principles like wave-particle duality, for example, technologies like laser systems, MRI scanners, the atomic clocks which make our GPS systems so accurate, these exploited basically the fundamental principles of quantum mechanics. And these were, so to say, in a way, technologies that used uh, quantum behavior for these applications. Now, the reason or the fundamental principle in which quantum technologies are different from the type of classical compute and communication technologies we use these days is it's quite simple in principle. For example, the way our microprocessors work is, you might know, in terms of binary 0 and 1, where a logical state of 0 is represented by the absence of a flow of electrons, for example, and a logical state 1 may be represented by a flow of electrons. So we are currently using technologies that control groups of subatomic particles and their behavior rather than individual atomic particles. Quantum technology is now the second revolution, basically. Oh, sorry, I keep going back to the previous slide. Okay. So quantum technology, the second revolution where we are, is becoming more and more important and interesting, because we are now able to control individual subatomic particles and manipulate their states to represent, so to say, logical zeros or ones or other states. So the ability to move from controlling a group of electrons or a group of subatomic particles to individual subatomic particles is what has made quantum computing that much more potent and capable in terms of addressing larger problems, more accurate, and increased speed. And so that's where you come across terminologies like superposition, entanglement, quantum states, their manipulation, etc. And primarily, the evolution of these technologies has driven the development of quantum communication and quantum computing more recently. So we are in the middle of basically, or we are in the start of the second quantum revolution, so to say. And quantum computing is just one of a group of technologies called quantum technologies. So there is many of the communication and work around quantum technologies more recently has focused around quantum computing, but actually things like quantum communication are far more advanced in the development and capabilities of the technology. And with the enablement of quantum communication and computing, Europe is heading towards what is called a quantum internet, where you would be able to process data using quantum mechanical principles, and then you would be also able to communicate them over good fair distances, terrestrial, but also terrestrial in space. So the coming togetherness, so to say, of quantum communication and quantum computing is what drives quantum technologies as a whole. And in this area as well, in this domain or in this paradigm of computing, again, there are strata of having to develop the fundamental engineering of devices, the control of these devices, and then the software and applications and algorithms that are around or are sitting on top of these technologies. And then naturally the skills development. The skills development is going to be very critical, because as I mentioned previously, the fundamental way in which we control the subatomic particles is what makes quantum computing different. And hence, the way in which we manipulate data, the way in which we probably assign values to a variable and define the algorithms and functions around how to manipulate variables is going to be significantly different compared to how we are doing it currently in our classical programming system. So the way in which problems are translated into algorithms and then they are implemented on quantum technical devices, that is where a lot of reskilling has to be done. The knowledge currently rests pretty much with people who are experienced in advanced linear algebra, in quantum physics, quantum information processing. Those are the type of skills that are required currently to translate problems into quantum computing devices. Now that has to be augmented with software and programming capabilities and tools. So it's kind of bridging two scientific and technical domains. One is the physics and mathematical driven quantum information science. And then on the other side is the computing science and the computer science. So these two domains and skills have to work hand in hand for us to be able to actually program quantum communication and computation devices and create applications and algorithms around these. We'll touch on that a bit later today as well. So, in terms of quantum computing, again, this is one of the slides which probably presents details that have been around for quite a good few years now. Quantum computing, I briefly mentioned, differs from classical computing in the way that classical computing works with discrete logic states of 0 or 1, whereas in quantum computing, we work with a superposition or a combination of 0 and 1. So we can represent a 0 or a 1 or somewhere in between all simultaneously with a certain amount of probability. So we can represent different states of information at the same time with fewer qubits, so to say, and the ability to process all of this at the same time in parallel is where the power or the performance capability of quantum computers stem from. Quantum computers are broadly of two categories. They are used interchangeably, but more recently, the news in quantum computing has been around what we call the universal gate models. But prior to them, one of the models that was practically and commercially viable was the model that you might be familiar with, companies like D-Wave, which are based on adiabatic or annealing-based models, where they are capable of solving a very specific category of problems, particularly around optimization, where you can find a minima of an energy landscape, for example. And so they were very capable, or they are very capable of solving a very particular niche of optimization problems. Whereas we are moving towards much smaller but more potent and general models called the universal gate models, which is what is circuit-based quantum computing from the likes of companies like Intel or IBM or Honeywell, for example, and so on. So there are different technologies, underlying technologies being used in terms of superconducting or tramp-ion-based spin topological. These are technologies that we use to implement and engineer quantum mechanical devices with which we can build then quantum computing devices. But this is basically a quick background. And where we are in terms of the evolution or the development of these devices is that with around, I think in the news more recently, we are talking about the higher order of tens of qubits, around 50 to 70 to even 100 sometimes. Now, each qubit is of different quality, so let's not probably go into the scientific or engineering aspects, but generally when we are talking about the order of a few tens or maybe even a few hundreds of qubits, we are talking about a technology that has become a reality in the last couple of years, and it has accelerated in becoming more viable. So with now, we are able to solve a certain category of problems. They are smaller problems like simulation or analysis of very small physics or chemistry systems, molecular systems. Nevertheless, we are able to address more these problems at a proof of concept level with increased accuracy and performance compared to their counterparts in the classical supercomputers. So for very specific problems, we are able to perform computations with better accuracy compared to supercomputers, while all of this in a larger scale is still in a smaller scale and proof of concept mode. To be able to work with smaller problems and increasingly larger production level or practical commercial applications, we are headed in the direction of quantum computing systems which have the capability of a few thousands or even few tens of thousands, million order of qubits. And these are going to be necessary to be able to address things like designing drugs using quantum computing devices, doing a significant part of the computationally intensive machine learning, deep learning algorithms, and so on. So this is a technology that has been rapidly growing. Nevertheless, it has to move on to larger systems to be able to solve larger problems. Now, in terms of the types of applications where quantum computing is going to be relevant, is foreseen to be relevant, this is probably, again, a heavily used illustration. This illustration, this Venn diagram basically presents the type of application domains and the types of applications where quantum computing is going to be relevant and suitable in terms of chemistry, physics, math, computing, biology, and so on. I keep saying where quantum computing is going to be suitable because, at least for the foreseeable future, quantum computation devices are going to be very capable of solving a select class of applications. They're not going to replace our laptops or our supercomputers or our cloud systems altogether, but they're going to function as accelerators that can solve very specific categories of problems very efficiently. So they would function alongside or be coupled to our existing classical systems. And so one of the main challenges has been to identify what types of applications, what type of algorithms are going to be better suited for quantum computing. And just to give a quick dive into a couple of applications where it's going to be really impactful, foreseen to be really impactful in terms of material sciences. For instance, what this illustration presents here is a material called vanadium dioxide. And this material basically transforms from being an insulator to a conductor when triggered by heat, light, or other stimuli. So a single material can be either an insulator or a conductor depending on how we trigger it. On the left is the picture of how it is when it's an insulator, where it's not necessarily well aligned. But then on the right, what we see is that once the atomic bonds are well aligned, it becomes a conducting material. And so the study of such materials and their behavior basically has a lot of application, even currently, in terms of creating devices with application in areas like sensing and infrared camouflage technology and materials where they are best suited and identifying materials that are best suited for actually developing quantum devices themselves. So material science is one area where the behavior of the physical system, the physics system, maps very seamlessly and symmetrically to how quantum computing devices actually function. So there is kind of a one-to-one mapping in the elements of a physical system onto the paradigm of quantum computing. So quantum computers are naturally well suited for these kind of problems. And similarly in chemistry, again, molecular structures, things like analyzing the interaction of carbon dioxide with absorbance, like in these graphene sheets. So graphene sheets, for example, are and similar molecular structures are usually studied for their capability to absorb or bind to carbon dioxide, to remove carbon dioxide from the atmosphere or from specific sources. So it's important to analyze and model and create the interaction between a carbon dioxide molecule and a very suitable or a capable absorptive surface. So again, since we are talking about the behavior of subatomic and even atomic particles and their characteristics, that kind of a study or application maps very well with quantum computing devices. And this is what gives rise to the notion of applying quantum computers to climate challenges or environmental problems or to drug design. This is the source where those kind of potential applications are likely to be possible in future. And then another well advertised area of application for quantum computers is optimization. So when we are talking about optimization problems, an objective to, so to say, partition a graph or analyze certain graphical analysis models like route optimization, logistical optimization, allocation of jobs to peoples or a limited amount of resources. These kind of problems where you need to search through a space of possible combinations, that's where quantum computing again can explore a very large search space in a more quicker time to solution fashion, but also with more accuracy. And this finds applications in many sectors, like in engineering, in mechanics, in economics, and in finances, for example. In all of these, what we see is that quantum computing is capable of working with increased accuracy and searching through or working along with searching through a very large search space with an increased performance and increased accuracy. So that's where quantum computing is going to be very potent. Another area where quantum computing has been tied to very much is artificial intelligence, and particularly in terms of machine learning. Yes, so quantum enhanced machine learning basically refers to quantum algorithms that can solve certain tasks in machine learning, thereby improving and often speeding up the classical machine learning techniques. And such algorithms are typically assumed to work with classical data that is actually piped or pumped into the quantum computing system. However, the primary challenge that quantum computers currently have, and that is yet to be solved, is the ability to encode a large amount of classical data, that is, pump the data that we have in our classical systems into quantum computing devices. So we can assume a quantum computer is something that has a very narrow input pipe and an output pipe. So the amount of data they can pump into the system and get out of the system, that's going to be very expensive. Whereas once you're able to get the data into superposition, and for problems like in material science and chemistry and optimization, the amount of data that you actually need to pump into the system for the problem to, so to say, explode in the quantum space, and then for it to do efficiently to computation, the amount of data that needs to go in and go out for these first three kind of problems is very small. Whereas typically in AI, in deep learning, we work with large input data sets, and then maybe the result of the inference or the analysis is relatively smaller. So working with larger data sets by encoding them into quantum computers, that is something that also needs to be solved to be able to work with large IO intensive applications. So given that for example, is where quantum computing is currently at, and what kind of problems it's immediately capable of solving better. Another key area where quantum computer and their ecosystem are being developed is how would quantum computing systems function alongside classical HPC systems? Because as I said, quantum computers are going to be capable of solving very specific parts of a larger problem. So what would happen eventually is that in our existing workflow of applications and solutions and software, very specific steps in the computation are going to be offloaded. For example, once we do the first two steps in classical computing, we may offload one of the steps like we do to a GPU currently. We might offload it to a quantum computing device and then get the results back into the classical pipeline and then iterate over this a number of times, for example. And so this is the way quantum computers and their applications are going to function alongside our existing HPC or classical software stacks and applications. Now, we are all familiar with or pretty much how the classical HPC stack is set up. At the bottom, we have a classical HPC hardware, which is based on CPUs or accelerators like GPUs, FPGAs, and so on. And then on top of that sits elements of an operating system, file system, and a number of system software capabilities. Now, these system software capabilities are typically hidden from the top layer. And then we, in terms of HPC or high performance computing or cloud devices, we have what are called these parallel programming models, which allow us to efficiently distribute and parallelize end user applications on these parallel hardware. So the parallel programming models in many cases are again hidden. It's for the performance engineers and people that are familiar with HPC that deal with optimizing an application's distribution and parallelization on the underlying hardware. Typically, developers and end users work with application development toolkits. They were predominantly C, C++, Fortran in many areas, but increasingly there is a lot of capability built around providing a programming interface through tools like MATLAB or through languages like Python and libraries with TensorFlow and SQL and so on. So this is the classical HPC or programming stack that we typically have been using for a while, and it has taken a long time for us to kind of arrive at this modular level. On the other side, quantum computing software stacks are pretty much almost similar. We have quantum computing hardware and very vendor-specific or even device-specific system software. We have a toned-down version, so to say, of CentOS that is able to run the applications or translate the applications that we write or programs that we write onto quantum devices. And then on top of the system software sit the programming toolkits that we might have heard about, the quantum software development kits like from IBM or from Atos or many other companies and research groups. And then on top of that, we use user applications. And typically the QSDKs, the quantum software development kits, they are built around these high-level languages like Python or MATLAB even sometimes. Now, the current status is that the quantum computing system and the quantum computing software stack sits in a sandbox. So we connect to a cloud system that is offered by a company, or we download a quantum simulator and software development package to our laptop, or connect to a HPC device, and then work just by creating some circuits, running some algorithms, for example. So all of this sits in its own environment as a sandbox. There is not real interaction or connection between a classical HPC workflow that's already existing, or a production application and a programming environment with the software stack of a QC system. So increasingly going forward, it's going to be important to have a more seamless implementation of our applications, where the classical computation kernels are written seamlessly with a quantum computation kernel in a similar fashion. For people that are familiar with accelerator-based programming, you might have some keywords or triggers or variables that you set in a function definition, and then you say run on a GPU or run on a CPU or run on a QPU, for example, and the target device and the kernel is basically offloaded to a kernel to the specific target device. So the end user application and the programming needs to be adopted going forward to have the quantum computing and the classical computing elements more seamlessly integrated. And that requires naturally the entire software stack at the bottom to also be integrated seamlessly. This means physically connecting quantum computing devices to classical devices. That has to be improved going forward for better I/O and better control flow between them. And naturally, the system software now they have to evolve to support both. And then the application software development kits. Currently, there are within Python, I think we have libraries through which we can implement both classical computational routines and computational routines that are specific to the quantum computing paradigm. So the blue layer is where much of the development has been helpful. The more important part going forward is to integrate how classical HPC specific libraries and tools are going to be able to integrate the quantum software development libraries and tools. So that's where much of the questions and work is going to be important going forward. There are certain activities that are coming up at a national and European level to address integration of these stacks. I'll come to that maybe towards the end of the talk, but this is going to be very important in terms of how we can leverage and demonstrate the practical capabilities of QC in an existing environment. And as I say, in many of the previous slides, I've said, this is upcoming, this is evolving, and so on. This is because, as we said, quantum computing is an area where the technology is constantly evolving. Even our classical computers currently are implemented, as you know, with silicon-based semiconductor technology. And in quantum computing, similarly, the methodology, the technology that is used to engineer and build qubits, which are the physical implementations of either a 0 or a 1 or a superposition in the quantum paradigm, the technology used for that is still undecided. The approaches that we see are using superconducting methodology or trapped ion or topological being explored and so on. These are still investigated by different companies, and often we see that academic research groups like in TU Delft or in the Netherlands or in the University of California, Santa Barbara, for example, they work with the likes of Intel or Google. There's close collaboration between academic researchers and the R&D teams within industry to find which of these technologies are going to be more suitable for developing higher quality qubits and hence higher quality quantum computing devices. So this is very much in flux. Each of them have different advantages and disadvantages in terms of the quality of the qubits that are produced, and hence the jury is still out, so to say, in which of these technologies is going to produce more stable and more higher quality qubits going forward. For all we know, more than one of these could be the winners for building quantum computing devices. Now, since we mentioned the performance of a quantum computing device, even the performance metric, for example, how would we measure the quality and performance of a quantum computer or a quantum device? That is, again, even the metric that is to be used is still under development. Initially, it was all around how many number of qubits can a device have, or a higher qubit was considered to be better device. But then the quality of a qubit came into play, the type of application, the scale of application came into play. So the metric, the quantity with which we measure the performance or capability of a device is also evolving. It has moved on from just a mere count of qubits to a notion called quantum volume. More recently, there are methodologies published around calculating a Q-score, which is an application-driven estimation of the capability of a quantum computing device. This again is constantly evolving. There are a number of bottlenecks and challenges as well. We have to migrate through them in the development of the technology. Decoherence is something that we might have seen. Decoherence is how long can a quantum device or a qubit basically be error-free over time, because when we store data basically as zeros or ones, even in our classical systems, they tend to decay, but then the technology in classical systems has evolved to an extent where the zeros or ones remain stable for a relatively longer period of time. So we don't have to worry about our data getting corrupted or wiped once we store it for longer. But then in quantum technologies, the duration for which a qubit remains sane or meaningful or error-free, that's relatively short. So decoherence is basically increasing the duration for which we can maintain a qubit to a correct value. That is where these technologies like superconducting, trapped ion, etc., they differ as well. Some of them can work with qubits much faster, but then some of them can maintain qubits for longer. So the speed versus stability is where these technologies differ. Again, error correction is something that will be implemented. It's already implemented in our current technologies at hardware and software level to be able to identify errors in the data over time and repair them at a physical level, but also in our applications. Similarly, in quantum technologies paradigm, error correction at hardware level and algorithmic level is something that has been developed quite a lot. Previously, I mentioned that currently quantum computing devices are in the phase of what we call NISQ and ISQ, noisy intermediate scale quantum devices. They have a challenge of not being able to work with large amounts of data being sent into the system. Where they are really good is when we are able to pipe in smaller amounts of data, but can explode the problem in the quantum space. So increasing, so to say, the ability to encode larger data into quantum systems is an active area of research and development, both in industry and in academia. And lastly, one of the one of the areas where there is much demand and impetus and interest is creating the learning experience and learning material around all of these technologies and development. Because on one side, we discussed in the beginning that the skills that are going to be required for quantum computing, particularly in quantum programming and its application, are going to be a blend of physics, mathematics, and software engineering. So to be able to build this kind of a skilled workforce, either through transforming the existing ICT skilled people to have a quantum computing conceptual and mathematical background, or to equip the upcoming physics and mathematical graduates who are quantum physics aware to be able to program, to either to bridge the spectrum is what is needed to have a quantum ready workforce going forward, both for R&D but also for exploitation in practical areas. So developing the learning methodology, the learning resources, either books or practical Jupyter notebooks, for example, and practical applications and so on. That's an active area where the learning material and the learning experience is being created. Now, we don't all have to jump headfirst into advanced linear algebra and algorithms. We can address it from either end of the spectrum, so to say, from the science or from the end use, depending on our background and the requirements of quantum computing in our area of work. So, for example, on the bottom right extreme one, the quantum computing and applied approach, It's a textbook that kind of balances the an application-oriented approach, as it says, to learning more about quantum computing. It kind of keeps the mathematics for the more technically savvy readers, but then everyone can get something out of it from reading it. These kind of learning materials. So, since we saw that potentially quantum computers are becoming increasingly relevant and realizable, and they have potential application in a number of areas, like in financial services and pharmaceuticals, in optimization problems which find relevance in engineering, for example. There are a number of target areas where quantum computers and their applications are going to be useful. The next question is, like, if we wanted to have access to learn or to do our own R&D, what kind of systems are available? One of the easiest solutions are software simulated quantum computing environments that are available from industry or even from some research groups. So these are simulated either on our laptops, which we can download from the net and install on our machines, or we can deploy them on HPC clusters for simulating larger scale quantum computing problems. So software simulated quantum computing devices are something that are quite easy to get our hands on. In most cases, they are license free. Now, physical quantum mechanical devices of limited qubits of the NISQ category that I mentioned, they are again available via commercial cloud services from different vendors. We might have seen many of them in the news as well. But then there's a lot of activity going on at a national level and European level, particularly, to build prototypes and initial implementations of physical quantum mechanical devices and couple them with existing supercomputing infrastructures and provide access to them for academic R&D, industrial R&D, and also skills development. So the Quantum Inspire there, for example, is a Dutch initiative where the National Supercomputing Center in the Netherlands have deployed an environment for access to academic researchers. We'll come to the EuroHPC, HPC-QS, and the QLP in a moment. The EuroHPC, HPC-QS is basically an initiative from the European Commission to deploy quantum computing platforms coupled to to two of the largest European HPC systems, where Ireland is involved as well. And the QLP is a national initiative where we are deploying a quantum learning platform, again, for national users with a wide range of programming and software development environments. We'll come to those in a moment. But then what's driving all of this at a national level? With a focus on quantum computing and quantum programming and software development. The Quantum Programming Ireland initiative since mid-2018 has been driven by ICHIC, the Irish Centre for High-End Computing, with our industry, academic, and public sector partners. This was basically in the context of seeing quantum computing as potentially the next giant leap in high-performance computing. So the initiative was to build expertise, to build a platform's capability at a national level, and to drive the national skills development as well. So the focus of the activity naturally is eventually on building hybrid HPC and quantum computing platforms, which would be accessible by Irish users, and then building the R&D experience to be able to develop algorithms and potential practical applications in this area, and to translate that knowledge, that skills, to the community in academia and industry through a number of skills development programs. So the initiative and the projects and the activities associated with it are funded through the government, through EU programs, and also industry engagement programs. And a quick word on who we are, if some of you are not familiar with ICHIC yet. ICHIC is the designated National Centre for HPC, High Performance Computing in Ireland. We are directly funded by the Department of Further Higher Education, Research, Innovation and Sciences. And we are hosted by NUIG, of course. And our primary area is in technologies which are associated with data management, data processing, and high performance compute. And to be able to provide platform access and services in these areas, and also to support the industry, public sector, and academia in access to these systems, but also provide our expertise in these technical areas to work as a bridge between the technology providers, so to say, and the technology consumers. So that's where ICHIC is positioned. A quick word on the National Quantum Learning Platform. So this is a platform that is becoming operational as we speak. It is intended to come online towards the end of quarter 3 or early quarter 4 this year. The objective is that the quantum learning platform will provide a software development environment for quantum computing to the end users that supports a wide range of quantum software development toolkits and programming ecosystems. It's meant to be vendor agnostic. So all the familiar toolkits that you might be familiar with, like Qiskit or Intel Quantum Simulator or Cirq or Tequila or a number of other programming environments, particularly for quantum computation, those would be deployed on the learning platform. And the learning platform itself would be integrated to the National Supercomputer K to provide this hybrid HPC quantum computing platform, which is very important as we saw, to get a better understanding of how would these hybrid systems be integrated, and then how would we eventually exploit them for application development and programming. This would be naturally, once it comes online, would be available for access to academia and industry users, both for skills development program and R&D. And the objective is actually to use the quantum learning platform as a stepping stone, as a national platform, but eventually to connect to the European HPC quantum simulation systems. So this is with respect to the Euro HPC program. If you are familiar with Euro HPC, it is basically the joint undertaking from the European Commission to build capabilities in terms of platforms, but also skills development and expertise across Europe, all the member states, in the area of HPC, AI, and high-performance data analytics. That's the purpose of Euro HPC. And one of the key activities in Euro HPC is the commissioning of 2 quantum computing devices, physical quantum computing devices, and integrating them in the largest supercomputers in Germany and France, and building basically the software stack, the integrated software stack of the classical HPC and quantum computing worlds, as I mentioned before. Now, Ireland, the consortium, this initiative is developed by by a consortium of 16 members. And Ireland is working with 5 other HPC centers across Europe, in Germany, France, Italy, and industry partners. So together, what we are doing is basically building the ecosystem at a national level through the quantum learning platform, and linking the quantum learning platform to these hybrid European HPC systems and quantum systems. Then the objective then is naturally to be able to provide skills support and R&D support to our national users. So for this, the Quantum Programming Ireland initiative actually started with engagement with our industrial partners, particularly around the area of quantum natural language processing and quantum chemistry. But then we're also working in a few other application areas. Just to highlight, the quantum natural language processing is around developing NLP algorithms that are quantum enabled for sentence similarity and their applications, like in auto contextualization or auto translation and so on. And in quantum chemistry, we work on problems where we study molecular structures which are environmental pollutants like PFAS. So PFAS are a long chain of carbon fluoro bonds, and PFAS are a category of substances which you can find commonly in your water-resistant materials, like in your cups, coffee cups, or a few other materials, because the CF bonds, the carbon fluorine bonds, are a few of the really strongest bonds, and so they wouldn't dissolve, and hence your cup remains kind of waterproof. But then the PFAS substances are extremely difficult to get rid of from the environment. They are a huge environmental pollutant. So the study of how to remove PFAS chemicals from environments or break them down chemically is of real environmental significance. So that is something that we are working on with European and national partners. In quantum chemistry, again, we work with an SME called Noritas in Ireland on studying mechanisms of how to efficiently encode peptide sequences, protein sequences onto quantum devices, and then potentially use them for the study of these peptides in the quantum paradigm. So these are some of the R&D programs, but what they eventually translate is for both iCheck and for our partners in the industry and academia to better understand how algorithms work in the quantum domain, what are the practical applications, potential practical applications that are going to be possible, and basically create a roadmap for developing our skills and capabilities and quantum-enabled solutions. That's the primary objective of the R&D activities. And as I repeatedly mentioned, skills development, all of this is translated. The quantum learning platform, the European hybrid HPC-QS system, and then the R&D, all of this is pooled into developing a skills development program called the Quantum Programming Certification course. This is targeted primarily at either quantum physicists and scientists who have the science background, but would want to get into quantum computing and programming, or the other way around, computational scientists, ICT skilled people who would want to get into the area of quantum computing, but need more background in the fundamental math and the quantum computing concepts and the algorithms. So it's to bridge these backgrounded people to come into the area of quantum computing and programming. And naturally, we will also be able to support the semi-technical or non-technical executives or employees in the general public sector or in industry to be able to get an understanding of what quantum computing and where it is going to be relevant, when it is going to be relevant, in what application areas. So with this objective in mind, the QPCC, the Quantum Programming Certification course, primarily focuses on 4 strands, which is presenting the fundamental concepts of quantum computing to be able to understand how does it function, where is it going to be applicable. Quantum computing systems, number 2, how are quantum computing systems built? What are the key elements and components in building a quantum computing system? And third, what is the ecosystem in terms of software and programming toolkits and the algorithms that are available and are being developed? And finally, naturally, all of this feeding into how can one watch the development of the quantum computing technology, how to identify trigger points, so to say, of where the technology is and where does it need to evolve to be able to address specific problems of certain size in certain areas. So it is important for us all at the end of the day to be able to understand, as the technology develops, what are the critical milestones, which then mean that they are going to be able to, quantum computing is going to be able to address specific problems or specific sizes. So to communicate these essential skills to the community is the primary focus of the Quantum Programming Certification course. And we are working on this together with Technology Ireland ICT SkillNet and an industry advisory board composed of 15 plus industry members, both from the quantum computing technology development, but also from the quantum computing end user industry across pharmaceuticals, financial sector, engineering sector, optimization sector, and so on. So for example, Nuritas, with whom I mentioned we work on a project, they are one example of a member of the industry advisory board. So the development of this certification course is actually driven with inputs from the industry advisory board and in partnership with ICT SkillNet. Because ICT SkillNet, they have a wide network and a very good understanding of how to engage with industry to elicit their requirements, which is key in the way this course is structured. And this course is under development, and we are aiming at a launch of starting the program from Q4 this year, and it's intended to run during the end of the year and beginning of next year. But then there will be subsequent iterations as well. So that was quite a lot that I tried to cover, but I hope each of you got something out of this whole spectrum of topics. In essence, quantum computing and in general quantum technologies, the real interest has been because something that was in theory and science a couple of decades ago has become more and more practical more recently and is rapidly evolving at an accelerated pace. And it's important to understand that it's a marathon, both the development and adoption of this technology, and we are just setting off. So thank you very much. And I'll be happy to take questions now, or if you would like to reach out later, we can have a discussion. Thank you very much.